Hello. Thanks for being here. Thank you for the organizers. Thank you to Fabrizio. I don't know. Oh, yeah. So I saw Fabrizio in Eat CC Cannes, what, 2 weeks ago or so, and he asked me if I could give a talk. Uh, I was a bit hesitant, and then I decided to say yes about puffs. I was very enthusiastic about it for a couple of days. I even told him, hey, can I do even longer than 20 minutes? And then he told me a few days ago, yeah, I got you a 40-minute slot. And by then, though, I was like, not so enthusiastic. I was like, oh man, what did I do? Why did I accept that? Um, Anyways, I'm gonna talk about a topic that I'm not a super expert in, but I do feel that our industry, when I say industry, like I come from the angle of blockchain and cryptocurrencies, there's a bit of a very low interest or very little awareness about it. And I think it's a very cool hardware primitive that is actually crucially important. And also you could say that from the point of view, because this is a quantum track, it's a bit in a way at the edge of classical computing and quantum computing. So you should take this presentation more as a sort of gentle introduction from someone who's not a super expert. So I think in what I'm going to present, maybe there's going to be pointers for you if somehow you're interested. The slides are online. I just put them up this week, so it's like, I'm probably going to try to improve them. But anyhow, so I hope you enjoyed this talk. And if you have any questions at some point, if you think you're totally lost, I'm okay to take questions during the talk. But yeah, I'll start and we'll see. Um, So yeah, it's an invitation to think deeply about secure hardware and how to hide secrets. By hide, I'll talk more about it. Oh, so another question you could think about is it possible to have secure hardware without physical one-way function? You don't have to answer now. I think it's a pretty deep question. Um, I'll skip this one because okay, the outline. So I'll go through the motivation, background context, um, then present puffs or physically unclonable functions, and then this proof of puff challenge is related to the problem of remote attestation, and for quantum cryptographers, that's device independent cryptography, like when you have certified source of randomness and all this. But in the classical computing, it's not as worked. It's not developed. The idea is not as thoroughly developed, I think, as in quantum cryptography. Okay. So a bit of context. Yeah, the context here, I come from the angle of trusted execution environment, like TEAS. So there's this, since we're in Napoli, yeah, a castle, they say, is a very old example of a T, right? Why? Because you have like security guards, and within the castle, whatever happened can be considered as trusted, and maybe people, let's say, write a letter in the castle and they seal it with some special seal, and then it goes out the castle, and then that envelope is kind of trusted. So I'll talk more about T's if some. So when I say we talk about T's, there are like three types, and in the blockchain industry, most people are more familiar with the Intel SGX, TDX, AMD SCV. But your mobile device has also a trusted execution environment. Apple is a secure enclave. With Android, it's a strong box. And if you use a credit card or if you have a hardware wallet, there's also a form of T in that. So basically, they're unavoidable. They're all over the place, whether you're in crypto or not. These T's or just all over on the planet. So what's the problem? At least from the point of view of blockchains, what the problem they try to solve is this problem of secure remote computation. So basically, you want to outsource a computation to a server that you don't trust, a service you don't trust, and you want to guarantee that they computed your, that they run the software that you expect on some hardware that you expect. And so the T's is a way to try to solve this problem with hardware. If you combine ZK, zero knowledge proofs, and FHE, you could say maybe you can try to solve the same problem, but there's like huge trade-offs, especially in terms of performance. So because of performance reasons, I think mostly people have looked into T's in the blockchain space. So yeah, like I just said that, they try to solve the remote computation. So security versus compute. So there's an interesting, it's very simple, but it's not hard to understand. But the more compute you want to do, the more security you have to give away. Basically, you have to sacrifice security at the expense of compute. So this little simple graph, what it shows that if your secure elements will be much more secure, but you'll have very low compute power. So people are then willing to do compromises, and especially in the Web3 blockchain space, they use things like Intel SGX and TDX, AMD. But if you talk to hardware researchers, they kind of scratch their head because this thing is just totally not secure from a hardware perspective. Whereas if you use a secure element on the other end of the spectrum, now they'll be like, okay, yeah, this is hard to attack. Okay, but for Intel SGX and the likes, I want to emphasize that because it's like I think it's really not well understood in the blockchain Web3 world because it's mostly people who do software and computer science. But again, I'm not a hardware researcher, but from talking with hardware researchers, they're very clear on that. They don't even want to spend time trying to attack Intel SGX because they don't see they don't see it worthwhile to get a paper out of it, basically, because it's just well known by hardware researchers that these systems are not secure. Mobile devices are kind of in the middle. They're actually more secure. So basically, the moral of the story here is that if you're trying to do something, you should really think hard about, do you really need something like Intel SGX or TDX? Because if you can, you don't need to compute that much. You can use much more secure hardware. Oh, it's not precise. I just like, yeah. It's just to show that the concept. Yeah. I'll skip this because I have many slides, but yeah, I will skip this one. So just briefly, the physical attacker models. So with servers, they kind of assume an obvious with maybe a bit of skills. With mobile devices, they assume an obvious, but maybe with some kind of bit like slightly expert knowledge, who could maybe manage to try to hack their phone, but they won't have any specialized equipment. Whereas with the secure elements and smart cards, they assume that the attacker would have access to a lab and all kinds of sophisticated equipment. And also, mobile devices and smart card, they are required to use some kind of certification and evaluation. It's the standard for this is called common criteria. It's not so important, but the point is that these goes through verification steps by a lab who will look at the security of the system. It doesn't mean it's perfect, but you still have this in place. Whereas with the T's that are used in the blockchain space, like by most projects, like Intel SGX and so on, there's no such thing. It's just the chip maker themselves, they try to make it secure, but there's no subsequent verification by an external party. By the way, this is all context, right? So, okay, the challenges of T's, right? It's you have secure key generation and storage and verifiable manufacturing and remote attestation. The attestation is linked to manufacturing in some way, but the main point is that all these systems, how they work, how they get their security is because there's a hardware, a key in the hardware that is embedded from which all the security is built. So it means if an attacker can get their hand on the key, the security of the system is totally compromised. The other problem is you have the same thing, I think, with quantum systems. If you have a photon source, how do you know that it's a legit photon source, right? How do you know that you're really talking to a quantum computer? Was it manufactured properly? Were there mistakes in the manufacturing process and so on? So one could say that the current T's, at least that people use, are really secure in a way because of economical reasons. So for instance, in the blockchain space, what people do, they say, okay, we'll run it behind the cloud, and they assume that the cloud provider will not try to hack the hardware. So basically, the data centers are like a castle with security guards, and they just protect what's inside, right? So basically, we need a balance. I think there's no way out of this. I don't, with quantum systems, I'm not so sure, but at least with classical system, you need a balance with cryptography, physics, and economics, right? Looks very complicated. Was just to show that how, for instance, SGX, this root of trust is derived. Okay, I don't know if I want to spend too much time on this, but what you should get out of this slide is that at the top there's these CPU fuses, and these are injected at manufacturing time by the chip maker, and from this all the cryptography is derived. So if someone can get their hands on that, again, they can forge attestation. Below there's a place where there's a quoting enclave where there's an attestation key. So that attestation key, you sign a report saying, hey, this is the hardware I'm running, this is the software I'm running, trust me, and this is signed. And the attestation key is trusted because it's signed by Intel. So it means there's this chain of trust. So it means if someone can get their hands on the attestation key, they can forge attestation report and say, hey, this is what I'm running, trust me, but actually they're running totally something different. If you know Mission Impossible, the movie, this is literally the same as these masks that they wear, right? And I will remove the mask and I'm totally someone else. So that's like an impersonation attack. So this is the crux of all this presentation I'm gonna try to present now, and why puffs are important and relevant to this context is that if we don't secure these keys, someone can just extract them and then impersonate hardware and software. So yeah, this SGX threat model assumes that, actually, by the way, that's what I was trying to say earlier. They don't assume that that it can protect against physical attacks or side channel attacks and so on. But yet people say, basically you cannot touch it, right? If you can access the hardware, it's like you have to assume that it can be broken or attacked by an attacker. So why is this? Okay, so now we're getting to the kind of maybe quantum related parts. Because you could say that atoms and bits are, you cannot separate. Information has to live somewhere. It's not just like, you know, so there's this quote here from Rolf Landauer that, right, again, the bits have to be encoded in matter and atoms and the spin of a photon in something. So you cannot avoid that. So that means that if you have a hardware key to protect from which all the security of the system will be built, and that it's in the hand of an attacker, so that means that the key is somewhere in the hardware. It lives somewhere. It has to be encoded. So that means that we have this challenge now, how to build hardware in such a way that even though the hardware is in the hand of an enemy, if you want, or someone you don't trust, and the bits, the atoms are there somewhere representing the private key, and it must not be accessible, right? So you could ask the question, okay, then how do you hide the bits and atoms? So that's what I came up with. Actually, you put them in a black hole. I think actually it's a good point, okay, because from the point of view of the problem of hiding a secret key such that it's not available to anyone, at least, by the way, there's people working on this idea in the sense at the theoretical physics and theoretical computer science, so it may sound a bit like just like a wild idea, but it is not that crazy in a way, because a black hole, you can see it as a one-way function. Of course, it's not practical, we cannot have that, but the point is just to illustrate the magnitude of the challenge, basically. Right? We have hardware on this planet that a lot of it, the security depends on a hardware key that is embedded in the hardware. Yet, depending on the means of the attacker, they may be able to access this key and compromise the security of the system. And here, what I'm trying to say here is that that may not be the only way, but just to give an idea of how challenging this is, yeah, if you could put the key in a black hole, then maybe you could say, okay, yeah, that's secure, right? But then you cannot use it, so it's another problem. By the way, there's a paper called Black Hole Radiation Decoding is Quantum Cryptography. I think it's very inspiring and interesting, and I encourage people to look at it. So, okay, let's say you say, okay, but I don't want to deal with quantum systems right now. I don't like Schrodinger's cat or something, right? So, okay, so we can look at puffs. Puffs are in the classical context. They're not in the quantum context. So Puffs arguably come from this work from 2001, was a PhD thesis by an MIT student called Physical One-Way Function. It's extremely interesting work. So I'll just now dive into this. I'll say what was the motivation, the inspiration, and the concept of physical one-way functions, and a brief note about the implementation.
So
their motivation, the motivation of the author was to one of the key questions they had is like, how do you
when you represent
money,
something that has value,
like cash,
in bits, how do you make sure that you can make sure that these bits are authentic. If you basically that's the doubles in 2001. So that's the double spending problem on blockchain. How do you make sure
you don't forge the token? How do you make sure you don't double spend? So he
approached
some of his work. The motivation was
this question.
Sorry. Another motivation was to have a fingerprint for physical objects. So basically, you would want to make sure that you have some object and it's really what it should be. Like, you know, you can have a serial number, but someone could try maybe to fake that serial number or to have a copy of it, clone it. So that was another motivation. How can you uniquely identify an object in such a way that it cannot be faked? Another motivation was to have a better understanding between the connection of physics and cryptography. Okay, so his key inspiration was quantum money. So this work, physical one-way function, that led to Puffs in a classical setting, were actually inspired by quantum money, which I think is very, very interesting. And the PhD thesis mentions these two works, conjugate coding by Wiesner and quantum cryptography, or unforgeable subway tokens by Bennett and others. So what's the key concept of this physical one-way function? Is basically you have a physical interaction between a physical object and a probe. So if you're probing a system, and that interaction would lead to some kind of like it would mimic like a one-way function. I'll explain more a bit in a little bit. And this has to be based on hard problems, basically that you cannot easily clone the physical objects, and that you cannot, what is this? Yeah, you cannot simulate the interaction between the probing and the object. And just like hash functions, right, it has to be easy to make but difficult to clone. And the interaction between the probe, yeah, it should be difficult to simulate, basically. So let me go to the graph here. So, okay, so in that work, what they did, they think of it like, let's say you have a kind of credit card-like little object, and you send a light to it, a laser beam, but you decide on an angle. So the angle you choose is part of just picking an input to a hash function. You could think of it like that. And then the light goes through this and it will be deflected because the object, right, the token has some little irregularities, and depending on the angle, the light will come out at a different angle, and they put a plate to receive the light, and it will create a spot, right? So in the middle, like this 2D speckle. So depending basically on the angle that you shoot the laser at, depending on the token itself, the 3D token, you'll get the 2D speckle will be different. And then they transform this to a hash using some mathematics. And that kind of mimics like a physical one-way hash function. Okay, that's the key work of this physical one-way function PhD thesis. So this then work led to Puffs. So there was this early work called Silicon Physical Random Functions, in which they changed it. It was called physical random function, but because of not to avoid confusion with PRF, pseudo random functions, they named it Puff for physically unclonable functions. And now the idea was to implement this, because the work I showed before was optical, right? So they wanted to implement this in silicon and integrated circuits. And it's very interesting here because they mentioned that they want to, make sure that a given integrated circuit, a given chip, right, is unique and you can identify it like a fingerprint. But also, they say it's a manufacturer resistant, that the manufacturer wouldn't be able to somehow mess with this process. This was around 2002, right? So, which is interesting. So to give a concrete example of an implementation of a puff, you have two wires here, and you think it's like a racetrack, right? With two tracks, two wires. And let's say an electron goes into each wire, just imagine it like that. And it's a race. Which one will arrive first? Even though they start at the exact same time, but because the wires are not exactly the same, they have irregularities that cannot be controlled in the manufacturing process. So basically the logic is the same, but the physical implementation is slightly different, like if you think of atom by atom. So one will arrive before the other, and this cannot be predicted. No one can know because it's too small to control. So the first one that, let's say if it's a left wire or right wire, you will set a bit to 0 or 1 and vice versa. So then you can construct an array of bits this way, and then you can have a key out of that. And then if you give inputs to that, you can then have different outputs. I don't know how I am with the time, but so going further into this world of puffs, are there questions right now or no? All right. So there's two types of puffs that mainly are discussed in the literature, strong versus weak. And the strong have been shown, well, I'll talk about this a bit later, but they have been shown to be vulnerable to machine learning attacks. And because of that, puffs kind of got a very bad reputation. But there's another type of puffs, they're called the weak, or puffs that are just used to generate keys. And if I go back to this, right, in the challenge part where you have this 0, 1, 0 and 0, 1, 1, these little green boxes, that's the challenge. And for each different challenge, you will get a different response. That's for the strong puff case. For the weak puff case, you would just basically remove this, or you would just use a very few challenges, or you would just use just one challenge that you kind of hard code. And because when you don't have this large set of challenges, you cannot train a machine learning model to try to guess then what the response would be. Like I said, they're theoretically promising, but they've been subject to all kinds of machine learning attacks. And the key generation puffs, they can be used to generate public key pairs, for instance. And they're used a lot, like especially in IoT devices. In IoT devices, there may be like 600 million devices deployed that use them. So what are some key properties that you want to get out of a puff? The main thing, it should be unique, right? The way to think about this is like a fingerprint, right? You have a fingerprint for a chip or an object, but here we're talking about chips. So basically, when a chip is made, you have this kind of unique fingerprint, which is just like think of it, a serial number, and that you shouldn't be able, if you make two chips identical in terms of logic, their fingerprint should differ, right? So that's the key thing. And you should be able, each time you query the chip, because the way this works, okay, this puff is like a circuit block, and the key basically appears when the current flows in the chip. So when there's no current in the chip, there's no key. So you cannot just extract the key. There's no key. So it has to be turned on. And when it's turned on, you should get the same key each time. So that's what this stability is about. Now, if you try to probe the chip, okay, you could use a microscope or something. Well, a microscope is a physical interaction with the chip, and that very physical interaction in quantum, I think, physics, you would say it's an observation, but that observation, you do it with an instrument, which is a physical instrument. So it will disturb the chip enough such that the response will be different. So basically, the output of the puff will be different whether it's observed or not. So if you're observing the puff, right, with some physical instrumentation, it will output something different than when it's not being observed, right? Does that make sense? Because the entropy will be changed. So basically, the instrumentation will introduce noise in the chip circuitry and environment, which will change its output. And the other property, very important, it's called unclonable, so you shouldn't be able to clone it. By the way, here there's this little quote at the bottom that says that the hardness of cloning is empirical, right? So if you wanted a theoretical hardness, you have to go to quantum physics. So in a way, there's good and bad chaos for a puff. Okay, so there's this process manufacturing variations, which is good, and then these environmental and variations and aging are problematic. So this puff thing, right? When a chip is made, again, because they're not putting the chip atom by atom, so each chip will differ from the other. So these process variations are what allows people to design these puffs. Now, when a chip is operating, there's maybe heat and other kind of physical phenomena happening, and this kind of introduces noise. So that means that it can kind of like change the output of the puff. So one example is the vibration of electrons. So that means that the response will be slightly different from one, each time you query the chip for its puff response. And then there's aging. As the material of the chip kind of like wears out a bit, the puff response will change too. So this leads to this thing that is called stabilization. Basically, you want a deterministic output that each time you query the chip, right, its fingerprint should, 5 minutes, all right, should always be the same. So the most widely used scheme that I know, that I'm aware of for the stabilization is error correction schemes. So that's a bit problematic because it introduces this step where they need to store some kind of metadata in non-volatile memory to be able to do this error correcting codes, apply the error correcting codes to the puff response, right? So when you turn the chip on, it will produce this, let's say, bit string, but from each time you do it, it will be slightly different, and they have this error correction mechanism to make the response deterministic. But in order to do that, they have what they call helper data that is stored in non-volatile memory, and this is an attack vector to attack the puff. And there's other ways, and a very interesting one is metal oxide breakdown puff, but then later on, the same authors attacked it. Anyways, this is an area of research, and I don't have much time now, unfortunately, to... Yeah, I talk about this metal oxide breakdown puff, which I think is very interesting. I'll say briefly because I think it's right. So you take two transistors, you apply voltage to them, like you stress them intentionally, and it will cause the metal oxide to kind of break down, and then they can detect that, and then the first one to break down will be set to a 1, say, and the other 0, and then you construct an array. And this will be permanent. It's just like at setup time, if you want, the first time this happens. And they managed to attack it. The same author, the same lab that came up with this puff, they realized using an electron microscope, they could see the little spots on the chip, like you think of a tattoo, right? So they could see that, and then they could restore the key. Okay, so I think I will end here then. So now there's okay, let's say I don't know if I've convinced you that puffs are interesting, but let's say, okay, you still have this problem that, yeah, the puff is hardware. How do you know that it's a real puff, or how do you know that it was manufactured properly and all that? So I think it's an open question. In quantum cryptography, that's what I mentioned earlier. There's this concept of device-independent cryptography. So basically, how do you know you're talking to a quantum computer that is remote? We have the same problem here. There's interesting work that looked at that in the past where you know, if you assume a malicious puff, what can you do still? This is just a note if you want to explore these questions and beyond. There's some interesting work that is from this friend of mine, Alex, and others at ARIA, which is UK research fund, and they're looking at puffs and other things from point of view of research. So this is an interesting, I think, picture that you see here, physical and global functions, but it's a much bigger context. At the top left, you have secure hardware, tamper-proof sensors. You know, you have quantum money on the right-hand side. Tamper-proof materials, verifiable reactions. So the point is that these puffs, okay, if they're engineered properly, despite the challenges like I just mentioned, could play a key role in many of the infrastructure we have, right, on the planet. I think that's, yeah, that's it.